Good afternoon, everyone. Welcome. Today we are fortunate and happy to have Brewster Shaw present 2 astronaut scholarship awards and today's seminar. Brewster earned his bachelor and master's degree in engineering mechanics here at UW in 1968 and 69, and then proceeded on to a very rich and varied career. He started as a combat fighter pilot, became a test pilot and instructor pilot for the Air Force, and then was selected as one of the first group of astronauts to fly on the space shuttle. He went up thrice, once as a pilot and twice as a commander. And then when he stopped flying, he stayed on the ground as a manager of shuttle operations and space shuttle program altogether. He then left NASA, joined the private sector, and worked in a variety of roles with Rockwell and eventually Boeing. So the entire career was in the aerospace field, and there is one word that Brewster himself has used to somehow summarize the whole thing, a word that I value more than many, many other words. Brewster has served the country for 43 years. In every position he has had. So, Brewster, thank you. Welcome.
Thank you very much, Professor Bonanza. Okay, thanks to all of you for being here. We have the special opportunity, as was mentioned, of presenting a very prestigious award to 2 students here at the University of Wisconsin-Madison. We have 2 new astronaut scholars in our presence today. The Astronaut Scholarship Foundation was founded in 1984 by the original Mercury 7 astronauts. Their goal was to ensure that the United States would continue to be the global leader in science, technology, engineering, and mathematics. Since 1984, astronauts from Gemini, Apollo, Skylab, Space Shuttle, and International Space Station have also embraced their mission. The Astronaut Scholarship Foundation partners with industry, universities, and individual donors to identify the most outstanding university students pursuing STEM degrees while executing original research, and to award those students with scholarships. The Astronaut Scholarship is known nationwide as being among the largest merit-based monetary scholarships awarded to undergraduate juniors and seniors. The foundation has awarded more than 900 scholars with scholarships totaling more than $10 million. However, the scholarships are not solely monetary in nature. The Astronaut Scholarship Foundation maintains a lifelong relationship with each scholar and provides them with mentors, opportunities for personal and professional development, chances to meet astronauts, executive industry leaders, and most importantly, a network of their fellow scholars. Now, let's meet the 2025 University of Wisconsin astronaut scholars, Nicholas Rienstra and Nathan Wagner. Guys, will you please come up? Congratulations, man. Outstanding. Way to go, you guys. Okay. These belong to you, guys. Don't lose them. Don't hang them in the closet. Okay. Would you like to say a few words, please?
Yeah.
Oh, yeah. Good thing. Sorry.
You gotta get in there.
Okay. Okay. Here we go.
You're the reason why they're here.
Nope, not at all. Okay.
Good.
Yes, sir. Have at it.
Thanks everybody for showing up. This is great. Obviously, thank you, Brewster. Thank you to the Astronaut Scholarship Foundation. They're amazing. I mean, I think I can speak for both Nathan and I and say that the connections and the opportunities that we've gotten thus far as scholars for 4 months, are just unparalleled with anything else we've had. in our experience as undergrads. And it's really a great accomplishment. I think it's a perfect accumulation of my work and research in an undergrad, and especially it aligns very well with my future goals in space and the astronaut corps. So,
Great.
Nathan?
Yeah, I completely agree. The ASF is an incredible organization. I'd like to thank everyone for organizing this event, coming out here and presenting these awards, and also to all of the 2025 astronaut scholars and the alumni, including Nicholas, for being just such an open, welcoming community. I had loads of fun in Houston meeting everyone, both the scholars and the organization, and yeah, it's an incredible honor to be receiving this award. So again, I'd like to thank the ASF Foundation. I'd like to thank all of the people I've worked with throughout my academic journey thus far. For example, Argonne National Laboratory, the Safman Group, Professor Walker, Professor Otten, and for all my family and close friends in the audience today, I'd like to thank you for being here and supporting me throughout my career thus far.
Okay, thank you very much, gentlemen. If you'd like to take those with you, that would be wonderful. Okay, are we ready? All right. I'll tell you what, these two guys and all the guys and gals that are part of the Astronaut Scholarship Foundation recipients make you really happy that you're not their age. The competition is incredibly tough. These kids are so bright, so motivated, so energetic. It just boggles the mind. Makes me proud to be an American. Okay, let's set the mood now by watching this spectacular video created by 3 crewmen on the International Space Station over a period of months. They did the filming over a period of months. They put it together after they got back. The music it's set to is written by Paul Simon. You'll recognize it. And the band that's doing this particular one is called Disturbed. Okay, let's roll it.
Hello, darkness, my old friend. I've come to talk with you again, because a vision softly creeping left its seeds while I was sleeping, and the vision that was planted in my brain still remains within the sound of silence. In restless dreams I walked alone, narrow streets of cobblestone, neath the halo of a street lamp. I turned my collar to the cold and damp, when my eyes were stabbed by the flash of a neon light that split the night and touched the sound of silence. And in the naked light I saw 10,000 people, maybe more. People talking without speaking, people hearing without listening, people writing songs of silence. Fool said I, you do not know. Silence like a cancer grows. Hear my words that I might teach you. Take my arms and I might reach you. But my words, like silent raindrops, fell and echoed in the wells of silence. And the people bowed and prayed to the neon god they made. And the sign flashed out its warning, and the words that it was forming. And the sign said the words of the prophets are written on the subway walls, in tenement halls, and whispered in the sound of silence.
Okay, thank you. Thank you very much. It always takes me a little while to get going again after I watch that. So, 8 billion people we just looked at. 8 billion people. How can we few flyers be so lucky? How can we be so lucky? We have no more innate right to that view than any of those other 8 billion people. So it's incumbent upon us to use our experience, that experience that we've been so fortunate to gain, for the benefit of others. Okay, when that video started, there was light up at the top and there was dark down here. And that line of demarcation is called what? The terminator. That's the terminator. And on orbit, you see the terminator twice times 16 times a day, because you see a sunrise and a sunset, and they both have terminators associated with them. It's something I didn't know until I got to orbit and saw it and said, geez, what do you call that? You know, and somebody like John Young, I believe, said, well, that's a terminator. So the intent today is to share experience in executing the Space Shuttle high-risk technical program, and to demonstrate that having a plan when you're this age is hugely beneficial, hugely beneficial. Okay, before we start though, I'd like to recognize two former UW students who played significant roles in space exploration. The first is Jim Lovell, who spent 2 years here before he went to the United States Naval Academy. He was selected by NASA in the second selection back in 1962. He flew Gemini 7, Gemini 12, Apollo 8, Apollo 13, and he passed away earlier this year. The second one is Laurel Clark, who got a BS in zoology and an MD here at Wisconsin. She was in the 16th group of astronauts selected by NASA in 1996. And she flew on STS-107 and lost her life when Columbia disintegrated during entry. Now, I need to make sure that you know that I'm a pilot, and this is my disclaimer. Okay, everybody starts someplace. I started on a family farm in Michigan a long time ago, and when I was in high school and thinking about college, I didn't have a clue what I wanted to do with my life. But I did know I didn't want to spend it on the family farm. So I followed my dad to Madison, Wisconsin. My dad was in the class of 27 in agricultural engineering, and I was in the class of 67 in engineering mechanics. Now, many great things happened while I was here at Wisconsin, and a lot of them have to do with timing, and timing is something that we have absolutely no control over whatsoever, but when it comes your way, you need to be ready to take advantage of it. So the best thing that ever happened to me here at Wisconsin is Kathy Mueller. She's been, well, I've been her husband. She's been my wife for 56 years now. So as you can see, it was a really good timing thing that happened. Now, the luck continues, however, because in 1965, I was invited to join this group of crazies, and over the next 3.5 years, it paid for all my college education. It allowed me to buy a car. It allowed me to live a decent life as a student. And I have, one of them is deceased now, David, the bass player. But the other two and I are still best of friends. Now, at one point, we had a different drummer than Charlie, and that drummer was a pilot. And he took me flying one day, and I knew from that moment on that I wanted to fly. It was one of those lucky things that come along. And so he taught me to fly. Another thing that playing in the band did was it let me get a pilot's license, and it let me buy a third of that airplane for $1,200 my share. And I used to fly that airplane across Lake Michigan back to the farm and land in the field, and then come back to fly it back over the lake to Madison, come back to school. And over the lake, you know, you just find the narrowest spot and you get as high as you possibly can until you know you can glide to the other shore, and then you can let down some. But it worked out great. So in 1968, there were 4 factors that played into the next chapter of the story. And I know this is supposed to be a seminar, but it's just going to be what happens, kind of. The first thing that happened was I love to fly. I learned to fly. I knew I wanted to do that. The second thing that came into play was the Apollo program was going on. This was the mid-'60s, and you know, you're watching all that happen thinking, oh boy, that's really high, that's really fast. Going to the moon would be great. I wonder if, you know, somebody else could do that. But gosh, it's pretty mysterious. How do they do that? And then the third thing was I took celestial mechanics from Professor Bud Schlack, who was like Professor Bonaza there, who was one of those people that just inspires you just by the kind of person they are, how they teach, how they relate to you, the interest they take in you as a young know-nothing. But after I finished celestial mechanics course, I said, I know how they do that now. I know how you go to the moon, because that's what it's all about. It's all about these equations of motion between orbiting bodies and all that. That's a piece of cake. Yeah. Now, the fourth factor was the one that forced the timing, and that was The draft board back in Michigan said, when you finish your master's degree, we're not going to defer you any longer. You are healthy, you're 1A. Oh, by the way, your lottery number in the draft lottery is in single digits. Have a nice day. Guaranteed I would be drafted, guaranteed I would go to Vietnam. The only question, or the only control I might have over anything is how I do that. How do I go to Vietnam? So I walked down to the Air Force recruiting office on State Street, and I said, what do you got? And they said, well, we'll offer you a delayed enlistment so you can finish your master's degree, and then we'll take you in and send you to officers training school. You'll become an officer, and then we'll send you to pilot training. Throw me in that briar patch. That's what I want to do. So that's exactly what happened. So in February, I went down to San Antonio, to Lackland Air Force Base, went to OTS, came back in May, married Kathy, and the next day she and I got in a car and drove to Selma, Alabama, to Craig Air Force Base for pilot training. Pilot training's a year long. So during that year, when we're living in Selma, Alabama, Kathy's teaching first grade in an all-black country school about 15 miles outside Selma, Alabama, and this was when George Wallace was governor of Alabama, and there was not integration. So for that whole year, I would measure that Kathy got the much better education than I did having the Air Force teach me how they want me to fly. So in March of 1973, I come back from Vietnam after 2 tours with my buddy Gary Reed here, backseater, and survived Vietnam. I don't have to go back again. The war is just about over. But the game that I was going to play in has changed because what? Nixon canceled the Apollo program, and we're not going to the moon anymore. But all of the space between here and the moon is still there, and there are some ideas about what to do with that. I didn't know exactly what they were, but I was pretty sure they were there. So I stayed in the Air Force. As Ricardo said, I went to test pilot school and became a test pilot at flight ops at Edwards Air Force Base. And then I was asked to come back to the school as an instructor, and I did that. And then in 1977, NASA rolls that baby out. And again, timing. No control over it whatsoever, but it just happens. And they needed crews to fly this thing because they had a few leftover Apollo people in the office, but certainly not enough to fly missions on things that hold 7 or 8 people and is going to do wonderful things in the future. So NASA, in their infinite wisdom, did a selection. And in 1978, they hired this bunch of 35 misfits. And you can see that there are 1, 2, 3 African Americans, 1 Japanese American, 6 women, and a variety of skill sets from all types of engineering to medical doctors to astrophysicists, regular physicists, chemical engineers, geologists, you name it. It's in that group of 35 new guys, TFNGs we were called. And the whole idea was that we were going to do these missions where you get in your truck, you load it up with your tools and what you're going to work on. It takes you to the work site, which happens to be on orbit. You do the job, you pack up, you come on back home, and then you get ready to go do that again on some other mission. But it's all mission-oriented. It's not commercial tourism like people are doing now. So, the space shuttle system hasn't flown in, well, since 2011, so 14 years, you know. Some of you don't hardly remember the space shuttle because it's not in the news. But it was a heck of a system. So, made up of the Space Shuttle Orbiter, which has 3 Space Shuttle main engines. They burn liquid oxygen and liquid hydrogen, both of which are carried in this big tank. Here's the liquid oxygen up here because it's heaviest, liquid hydrogen down here, but you need more of it volume-wise. The tank is the only thing that we throw away. Everything else is reusable. These solid rocket boosters are things of magic. They are bolted down to the launch pad by 4 big bolts on the bottom of them. That's the only thing that holds this thing up. They are made of segments that are poured liquid propellant into the casing out in Utah, and it sets up, becomes solid, and then they ship these on rail cars to Kennedy, and down at Kennedy they put them together, and the joints that they have to join at Kennedy are these, and they're called field joints because they're joined together in the field. These rockets are the liquid propellant, which becomes the solid propellant, it doesn't fill it up. It's hollow in the middle. Hollow in the middle. And the shape of it is like a star because the propellant, or the amount of thrust that these generate, is determined by the surface area that's burning. Okay? And so as this thing burns from the center out, the star shape keeps the surface area constant. And that lets the thrust of the solid rocket booster be constant until it burns out to the sides of the casing, and then it's all over. There's no more thrust. It goes out. So they are ignited by a little rocket motor that sits up there and fires its exhaust down through the middle, and so it ignites the whole thing at the same time, which means that in about 280 milliseconds, the thrust level on those goes from 0 to 90%, and then it flits around up there for the rest of the flight time. And they last about a little over 2 minutes, and they put out 3.3 million pounds of thrust each. That's a lot of thrust. These 3 rockets right here, or engines right here, put out about 1 million pounds between the 3 of them. So 7.5 million pounds of thrust at liftoff, and the stack weighs 4.5 million pounds. So that's pretty good thrust to weight ratio, and it gets out of town smartly. Okay, as I said, this is the only part that we don't use, so when we get rid of that, when it separates from the bottom of the orbiter, we have to be suborbital. Suborbital. So this will re-enter and burn up and fall in the ocean. Okay, so the 2 solid rocket boosters, the 3 main engines, and then right there, pardon my shakes, and right there are 2 little engines, 6,000-pound thrust, and there are 44 reaction control system thrusters that are in the front end and the back end, and those are to maneuver on orbit, to do the separation burn from the external tank when you get off, and to do a deorbit burn when you're getting ready to come home, or change orbit, something like that. We would use these OMS engines for those, and the rest of the time, attitude control is done by the RCS thrusters. Okay, so this is the White Room. You've heard of the White Room before. This is where you climb up or you ride up the elevator and walk across and get in the flight room, or the White Room, and there are about 6 people there waiting for you, and they help you strap in, hook up your harnesses and everything, hook up your oxygen, your radio cords and everything, make sure everything's okay, and then they leave and close the hatch on the side, and they get the heck out of Dodge. And this is the only time you go out to the pad when it's quiet out there, other than the noise of the fact that this thing is full of cryogenic fluids, and it's making all kinds of popping and banging and noise because the aluminum is stretching, shrinking, etc. So the first time that I got to go, it was a week before launch, and we were getting ready to go into quarantine. The whole crew goes into quarantine together, and then you go down to the Cape for the last couple days in quarantine, so you don't want to get sick on orbit. This is a surprise. The morning I'm going to go to quarantine, you know, have breakfast and gather up my stuff and head out the door to walk down the stairs to get in the car, and my 7-year-old son says, "Well, I guess you're going to go die now, Dad." And I stopped in my tracks, and I turned around and walked back up to the kitchen and said, "Come on, Brandon, come with me." And we went up, and by the time we sat down at the table, I thought I had figured out where that came from. And where that came from was, you know, we'd been training for a year, and John Young, who was the commander on this flight, and I would fly ascent after ascent after ascent in the simulator, and some days it would go well, and some day the sim supervisor would throw something at us that we or the team or the system couldn't handle, and we'd blow up or we'd crash or something like that. And I'd come home, and over dinner I'd tell Kathy about how the day was, and you know, well, we died in the simulator again today, and I killed us because I did this wrong or that wrong, and my 7-year-old son didn't know how to differentiate between simulation and real world. That was a hell of a big lesson for me. One other thing I want to say about that is the guy sitting over on this side of the airplane was the commander, and that was John Young. And you all know John Young went to the moon twice, once he went around it and once he landed on it. And he flew 2 Gemini, 2 Apollo, and 2 shuttle missions, including STS-1. John was the most intuitive engineer I've ever met. He just had a sense about him, from an engineering standpoint, what's right and what's wrong, what's true, what's not. It was amazing to watch him operate. At the same time, he was an incredible mentor to somebody like me. You know, we would be in the simulator and we'd be flying an ascent, and something would go wrong, and I would take action based on what I thought the signature of the problem was and what the checklist would say if you looked at it, but you didn't because you had ascent stuff memorized. And then the run would finish, and John would look over me in a very calm voice. He'd say, "Why did you do that?" And I'd try to explain to him, you know, the signature that I saw and what I thought the failure was. And he said, "Well, okay, but did you notice this over here? Did you see that this was happening or this signature was there?" And I thought, God, no, I didn't. But that's all he'd say. He'd just say, you know, ask me a question, and we'd talk about it. And he never told me what the answer was. He always made me get to the answer myself, but he led me to the answer. Incredible guy. Okay. So, see that right there? That's the exhaust coming out of the top one of those space shuttle main engines. So it's putting out 300,000+ pounds of thrust right now. And there are 3 of them. And remember, when they light, you're still strapped to the pad. You're still fastened down. The solid rockets are still bolted down. So you've got this 1,000,000 pounds of thrust kind of pushing the stack this way. So the stack bends, and the nose of the tank and the nose of the orbiter moves over, you build up all this stress in the tank structures, and then it kind of springs back. And when it springs back to the point where that stress that's in there gets very low or low enough, you blow the bolts that hold the thing down, and you ignite the solid rocket boosters. Now, when the engine's light, but not the solids, you can't really hear them. You're in a pressurized cockpit, and you got a helmet on and everything, but you can feel buzzing in the structure. And that's because those three main engines have great big turbo pumps in them, pumping liquid oxygen and liquid hydrogen, and they're spinning a gazillion RPM, and so it makes the whole structure buzz, and you can feel that. And then, when the solids light, it feels like somebody, bam, hit the back of your chair with a sledgehammer. It's really sharp because 280 milliseconds is not very long to put that kind of force on the thing, and it's shaking like that, and you're slammed back in the seat, and it's an incredible sensation, especially numero uno, the first time, when you don't know what's coming, and nobody's really told you this before. I don't know why, but it's really a surprise, and it is just shocking, and it just carries you away, and you just think, God, let the pointy end stay forward, because there's nothing you can do, and literally there is nothing you can do about it. As long as those two solid rocket boosters are burning, you can't affect anything. Now, you could declare an abort, say RTLS, but nothing would happen until you get off those solid rocket boosters, because you can't maneuver those things. The forces on the structure would be way, way too great. And so you just along for the ride for the first couple of minutes. Sound-wise, when the solids light, yeah, boom, that's really loud. But you come off the pad real fast, and then that sound kind of gets, it's not reflecting up, and you're not hearing it as much. So in ascent, the place where you really hear the sound is when the vehicle accelerates to what's called maximum dynamic pressure. And that's when the forces on the structure from the airflow, from you flying through the air, is maximum. As you accelerate, it wants to increase. As you climb out of the atmosphere, it wants to decrease. And so there's a point where it spikes. And at max Q, which is a call that the ground makes to you simply as a radio check, because you don't do anything about it, but they always call max Q, that's when it sounds like you're standing in a hurricane or a tornado, because it's a rough vehicle, and so the sound of the wind noise of the flow over the vehicle is just really, really loud. Another thing that surprised this one. Okay, so that's our ascent trajectory. And that ascent trajectory is a result of a bunch of smart engineers who have figured out how to maximize downrange velocity while controlling loads on the structure, right? You want to go horizontal, tangential to the Earth's surface. That's what's going to get you in orbit. But you don't want to do it low, because there's too much air, too much heat, too much drag. You waste energy, the structure gets too hot. So you have to get up out of the atmosphere, but also go downrange at the same time. And so that's a result of the analysis that they do to get the performance you need out of the limited amount of propellant that you have on this thing. So it's controlling drag, it's controlling heat, it's optimizing the downrange velocity, and when you come off the pad, the vehicle's sitting with the tail pointed south. Sits on the pad like that, tail pointed south, but you're going that way. So as soon as you have tower clear, the vehicle starts this eigenvector. Everybody knows what an eigenvector rotation is, right? 3-axis rotation. It starts this rotation, and if you go due east, your launch inclination, or your orbit inclination. You know what the orbit inclination is? The angle with the orbit plane against the horizon, or not horizon, the equator. It would be 28.5 degrees because that's the latitude of the launch site in Florida. And if you go straight that way, then this point, the top part of the north part of your orbit is always 28.5 up, even though the Earth rotates underneath it. But if you roll more and you steer further north than east, you can adjust your inclination to up to, we flew as high as 57 degrees inclination. And you do that right now, right when you're coming off here, because you don't have any velocity already generated that you have to bend or steer. You know, you're getting all of that stuff for free, plus the 1,000 feet per second that you get because the Earth happens to be rotating. So you establish that right then. And so it flies at 2 minutes or so. You get rid of those big solid cases. They tumble into the ocean. They get towed back by boats and disassembled and sent back to Utah to get filled up again and reused. So you get up there, you're high enough now, and you have generated enough velocity, which is about 17,800 miles an hour or 25,800 feet per second, depending on how you think about that. And you get to this target, and then you have MECO, main engine cutoff, MECO. As soon as you do that, you can take your pencil out and you can let go, and it floats. And you float. If you take your seatbelt off, everything's floating, because you're all falling towards the center of the Earth at the same rate. There's nothing there that causes any forces, no lift, anything like that. So you're all falling together. So you and the spacecraft that you're in are all falling together, and so it's 0G. You know, so you don't have any relative motion unless you push off the wall or something like that. Wonderful feeling. And it just happens like that as soon as the engine shut off. It's pretty cool. Okay. So, whoops, one too many. Here we go. We get on orbit. We separate from the tank. Remember I said we would be suborbital at that time. So soon after we get off the tank, we use those 2 ohms engines and do a posigrade thrust, and we raise perigee, which is on the other side of the Earth right now, and it circularizes the orbit. Let's put the orbit in perspective. The Earth is 8,000 miles in diameter. That's 8,000 miles. We are on a nominal shuttle mission 150 miles up. That's less than this little finger above the surface of the Earth. And beneath us, starting about halfway down, is where the top of the atmosphere starts. And so all that stuff is in this, like that. So when we're in orbit, we are in orbit just barely above the surface of the Earth. And so when you do we get off, we let the tank go here, we're going to do a posigrade. That's going to make the orbit higher over here. Not here, we're just going to go faster. But what that does from orbital mechanics is it makes it orbit higher over here. And so we do that. And we circularize the orbit, and then on most missions, it just stays like that until the mission's over and it's time to come home, and then we'll talk about deorbiting in a minute. Okay, so we're going to configure the vehicle for on-orbit. We open the payload bay doors, right? And we want to get those open because there are radiators on the inside of the doors, and that's how we get rid of the heat that we generate inside the shuttle and any payload that's attached to it. We get access to whatever payload we have in here, which is just dictated by whatever the mission is. You know, if we're going to deploy things, we will be able to deploy them. At the time, we can get out the remote manipulator system, bless their hearts, from Canada, and we get ready to go to work. Now, we have to take care of the software because the software got us on orbit. There are 5 general purpose computers, which are IBM 101 computers, that are the main brains of the shuttle system. And the shuttle is all fly-by-wire. The whole thing is fly-by-wire. So 5 main computers, and then there are a whole bunch of smaller computers all over the vehicle that are attached to sensors and effectors and those things, and they all talk to these 5 computers. 4 of the computers have the same software, exactly identical software in them, and it's called PASS, primary software. And it is written in HAL, code was the code, and this software in these things, they all talk to each other, they compare answers all the time, and when one of them gets an answer that's different than the others, it gets voted off the island. And it goes to sleep, and it's no longer functional until you do something about it. And there's a routine that will gracefully work its way down until you're flying on only one of these computers, but you hope that doesn't happen. Now, if you have a generic software failure that we didn't catch in the verification, then the 5th computer has totally different software in it called backup flight system, so BFS. So there's a button on the commander's hand controller, and it's a red button. And if you push that button, these 4 are out of the game, and this one person or this one computer is doing it all by themselves. And that's all verified in testing after testing after testing on the ground in the SAIL, Shuttle Avionics Integration Laboratory test facility. So we have just flown Ascent. All of that stuff happened, and it's all been handled by these 4 computers. The RAM of these computers, 128K. Think about that, you smart programmers, right? Who could do that today? Those guys and gals were really smart software engineers that could put all of that capability in 128K. Then we got a little bit nervous and we paid IBM a whole bunch more money, and they doubled it to 256 for the rest of the program. But so we have 4 computers during dynamic flight running the ship on orbit. We have 1 computer running the ship, flying the ship. We have 1 computer that has entry software already loaded in it. We do that, and then we put it to sleep so that we can get access to that entry software if something should happen to both of our mass memory units, which are tape drive mass memory units, really, 70s technology, which the whole thing was 70s technology. And then a 3rd computer is made to run all of the payload stuff, not any guidance and navigation stuff. And then the fourth one just is put to sleep. But the BFS is still there, should you need it. So we changed the software, and we're ready to start working. So we can also go out EVA and do a lot of work there if the payloads, whatever the payload is, needs it. And that's really handy because a couple of humans out there can do things that you can't do robotically. So we use that capability a great deal. And they've got all of these kind of tethers and workstations and hookups and everything. But they also have this thing called SAFER. And this was designed and built by the folks at the Johnson Space Center. The whole purpose of this thing is that the shuttle itself, when it's alone, it's very maneuverable. And so if somebody, and it's happened to us before, if somebody gets untethered for some reason, then, and they start to float away, the shuttle, you can just point the bay at them and go over and scoop them up, and they can retether themselves, and you're good to go. But if you're docked to the International Space Station, which are 2 pretty good-sized, pressurized containers, and they're docked together, you can't simply, quickly disconnect them. You have to close hatches, you have to configure things, you have to make it safe to do that. And so they built these things so that they would have a jetpack mounted on the back of their EVA suits. So if they get loose, they can fly themselves back and reconnect to the space shuttle or the space station, whichever is the appropriate thing for them to do. Okay. So we carried up all of this stuff in the space shuttle one piece at a time. Lots and lots of flights, lots and lots of assembly operations, most of which had never been assembled per se on the ground. You know what ICDs are, interface control documents? If you use those to the T, things fit when you plug them together. If you don't, you can have trouble. We didn't have any trouble in assembling this whole thing. You know, it'd be a flight for that, a flight for that, a flight for that, flight for that, flight for that, etc. Flight for each one of these. And this stuff back here, not including that, that's part of the US segment. This stuff back here is Russian segment. It all came up on different vehicles than the space shuttle. We have a cupola, which is on the bottom looking down, and that's how those guys got those great pictures that we looked at. And we used a lot of EVA in doing this assembly over about a 10-year period that it took us to put it all together. So, besides doing, I told you that the ISS, I think I told you it was at 51.6 degree inclination. And the reason for that is because all of this stuff came out of Russia, which is at a higher inclination, and so we had to meet them halfway there so they could get their stuff there and we could get our stuff there. So 51.6 was where it turned out to be. We also did all kinds of deployments with the space shuttle on these non-space shuttle flights. All kinds of science, a lot of national security on one of my missions. My last one, it was a national security payload, which is classified. I can't talk about it. But in the space station, we did lots and lots of research on all kinds of things. This is just an example about some human things. We got some free research because of something called the South Atlantic anomaly. Anybody know what that is? The South Atlantic anomaly is a phenomenon that exists where over the South Atlantic and a little bit of South America continent, the magnetosphere, which is, here's a pole, and it goes like that. Well, at the South Atlantic anomaly, it goes like that. And it goes down far enough so that at 150 miles or 250 miles like the space station, you're flying in the area that is influenced by that. And what that allows to happen is heavy particles that are bombarding the Earth that normally end up at the poles because the magnetosphere takes them that way, they can come through your vehicle, and when they go through your head, you don't see, you experience. It's not coming through your eyes, it's just in your head, this flash. That's what happens when a heavy particle goes through your brain. I know that from firsthand experience. On STS-9, that first flight, we were at 57 degrees, and so we were high enough latitude to get into the South Atlantic anomaly. So, people have studied that. The docs, oh, wow, that can happen to you. Let's see what that means. Okay, how are we doing on time? Oh, boy, we got to hurry up. I'm sorry. So let's get to deorbit. Time to come home. We're in a circular orbit. Nice circle around the Earth, really close. Here's the Cape. We want to land there. So about halfway around, we turn around so we're going backwards, and we burn the OMS engines a little bit, retrograde, which means against the direction you're going. So you're going to slow down. As I said, we're doing 25,800 feet per second to be in orbit. We slow down about 250 feet per second. Little bitty like that. But what that does is you're slowing down here. That means this gets lower. And it gets lower enough so that up here someplace, as you're going around, you start getting into the top of the atmosphere. And once you start getting into the top of the atmosphere, drag takes over, and drag becomes the big mother and drives everything after that. And so the vehicle is very smart. It's on autopilot. George is a great pilot. It flies itself. It's 40 degrees nose up as it enters in, and it's controlled so you don't come in too fast, you get too hot. If you come in too slow, you skip. And then the next time you come in, you have the wrong conditions to make it to where you want to go. So you control the rate of descent by bank angle, and you also steer a little bit. If you have to go land over there, you want to, by the time you get down to about 40,000 feet, you want to be overhead the landing site. And you're going to be, by then, you're going to be subsonic, just subsonic, and the commander takes over and flies the pattern and the landing. It works really well. It's a great light show when you get into the heating of entry, you know, red light all around the vehicle. And you can't look out the back because the payload bay doors are closed, so you can't see it there. One thing that happened on STS-9, and this is an shucks on the government side, is that John and I told you we fly all kinds of things in the simulator. We have a shuttle training airplane that you can fly from 40,000 feet down, and it's an airplane, and you know it flies just like the shuttle, but you don't land. And so you get to right eye height, and it clicks off, and the instructor pilot that's over here takes it around and flies it up and sets you up again, and you do it again. But you don't land, and so you never derotate the vehicle. We only do that in the simulator. You land on the mains, you roll a little bit at the right speed, you put the nose forward gently, and it comes down and touches down on the ground. And that, between here and the vehicle motion, is due to the gains that they have in the control system. Well, on STS-9, they changed the gains and they didn't tell us. And we never saw it in the simulator. So John had no idea. So John had this technique of starting the nose down and relaxing back to detent. Instead of the nose stopping, it would just gently fall through. Well, on landing day, John starts the nose down, comes back to detent, and the nose stops. What the heck? You know, what do you do? Well, you got to get the nose down, so he gets back into it. And by now we're slow enough that when the nose comes down, it falls. And, you know, enough for the guys down sitting on the middeck, hey! And poor John, you know, I felt so bad for John because he is a consummate pilot, and he does all this stuff exactly right, but this was not right. And that was because we didn't communicate properly, and the planning of updating the software in the simulator didn't happen properly. Okay, I want to quickly, and I promise it will be quickly. Oops, there we go. Oops, there we go. Here is a summary of the 30 years of space shuttle flying. And I want to talk about Challenger and Columbia briefly. And these are my words from my observations and experience. In the face of the unexpected, When the pre-established planning and rules are not sufficient, human judgment may be applied, sometimes must be applied. That creates the potential for mischief. Strange way to describe it. And why? Because we humans are imperfect. Every significant accident is the result of a chain of events, any one of which, if interrupted, can preclude the accident from happening. You have lots of opportunity to keep it from happening if you're paying attention. So the lessons that we just demonstrated to ourselves again and again, but which apply to all high-risk technical endeavors, are listen to your hardware, you never know enough, maintain the proper priorities, let the data lead you, don't fail alone, meaning if you need help, for heaven's sakes, ask for it, don't be embarrassed, and don't try to do it on the cheap. Challenger was the failure of the field joint that I pointed out, because the field joint has two O-rings in the tang and clevis that fit together, and those O-rings, when you start the engine, when you ignite the engine, those O-rings are not always sitting exactly where they need to be in their little cavity. And so this high temperature, high pressure exhaust comes flying in there, and it pushes the O-rings into where they want to go because they go with the flow, and the flow is going out the hole that's there until they get in place. So it pushes them in the right place, and it seals up, and everything is hunky-dory, unless it doesn't. And on more than 10 cases, when we got this SRB cases back and took them apart, we found that we had O-ring erosion on those O-rings, which are not supposed to happen. And the engineers would sharpen their pencils and analyze it again, and they would say, oh, if we've got it bounded now, you know, it'll never be more than X. Well, the next flight, it's X plus Y. Oh, we'll do that again. And that went on, and eventually we started a redesign of the joint, but the program didn't stop. The program kept flying, and that cost us Challenger. On Columbia, we had more than 7 cases of bipod ramp flow foam. The bipod is the front of the orbiter where it attaches to the external tank, and then it comes out like that in a Y and attaches to the nose of the orbiter. And these are all foamed because you don't want ice to get on there if it's cold outside, and because ice is heavy, right? Foam is really light. And so a piece of foam would come off, and we saw impact indications on previous flights, nothing like on Columbia, but a piece of that foam came off, and because the vehicle is going so fast, the foam was doing about 500 miles an hour when it hit the leading edge, the RCC, reinforced carbon-carbon, on the leading edge, and it went right through, made a hole there, and so the hot plasma during reentry can go in that hole, and the hot plasma is 3,000 degrees, and this thing is made of aluminum, which doesn't take 3,000 degrees, and so it destroyed the vehicle from the inside, and we lost the Columbia and the crew. And the program did not ground the fleet in either case, even though that hardware had been talking to us for a long time. So, in summary, the space shuttle was a technical marvel in its time. It was also an imperfect system that ultimately couldn't live up to the expectations of operability and cost. Yet it accomplished a great deal for America and the world. It was, in many ways, a role model for the development of significant commerce in space. More than all other space launch systems combined, it has offered humans the opportunity to witness the wonder that is our Earth. Thank you for your attention. And congratulations to you guys.
We're running out of time, but if there's a couple quick questions, we could probably field those. So if anybody has a question? Yeah, or you can come up and talk to Bruce.
Yeah, I'm sorry I didn't make that clear. I know that some people have to leave. If others of you would like to stay and chat, I'm happy to do that. Sorry.
It's great to hear.
I was just so relieved that it was over.
Thank you very much. I'm Nicholas's father, Chad. Nice to meet
It's a
you.
pleasure.
Yeah,
Pleasure to meet
I'm actually
you.
a biochemistry professor here.
Are you really? Great.
But what I do, I also build nuclear magnetic resonance spectrometers.
Really?
Yeah. And so I deal with cryogenics and healing recovery systems.
Yeah.
And we have a big facility right across the street in the biochemistry building. It's
Got
one
it.
of the largest in the country. It's called the National Magnetic Resonance
Oh,
Facility.
yeah. I've heard of that.
Madison, yeah. So I moved here from Illinois. When we moved 5 years ago, I was a professor in chemistry at Illinois.
Okay.
We moved here when John Markley retired.
Okay.
Who was the professor who established that facility. So,
Okay, so do you like working on this?
oh, it's great. Yeah,
Good,
Yeah.
good.
I've actually now started a company